Have you ever wondered why nothing, absolutely nothing, can go faster than light? Not a rocket, not a particle, not even your wildest imagination. It's a rule written into the very fabric of the universe. But here's the thing. What if the reason isn't just it can't happen? What if there's a deeper, stranger story hiding beneath the speed of light itself? You're going to see the universe through his eyes, a universe where intuition fails and curiosity is your only compass. Now, you probably know me as the physics genius who danced through quantum mechanics like it was a jazz tune. You might know about my Nobel Prize in 1965 for uncovering the secrets of the quantum world, or my eccentric love for bongo drums and safe cracking. But what most people don't realize is that my true obsession was understanding the very limits of reality, why the speed of light c is the ultimate cosmic speed limit, and why that boundary is more mysterious than anyone ever told you in school. Einstein dropped the bombshell over a century ago with his theory of relativity, special relativity to be precise. In its simplest form, it tells us that the faster you move, the heavier you get, the slower time flows for you, and the universe reshapes itself around your motion. And there's one number at the heart of it all: c, light speed, the cosmic speed limit. Nothing can surpass it. Not matter, not energy, not even information. But here's where things get weird, really weird. Because Einstein gave us the rule, but he didn't exactly explain the why. And that's where I come in. I was the guy who loved asking the questions that made other physicists squirm. I'd peer at the equations, at the experiments, and I'd say, wait a second, that doesn't feel intuitive. How can time slow down? How can mass increase? Isn't that impossible? And when you think it's impossible, that's exactly where the universe starts to reveal its secrets. Now you might think, okay, so nothing goes faster than light. Got it. But stay with me. There's a story here, a story about thought experiments, about bouncing electrons off of imaginary walls, about questioning what reality really is. There's a reason I could sit in a New Mexico desert playing my bongos and suddenly understand a principle that had stumped the greatest minds for decades. Curiosity, relentless curiosity, is the key. And that's exactly what you're going to experience in this video. By the end of this journey, you won't just know that nothing exceeds c, you'll understand why, you'll see how space and time bend around motion, how energy and mass are intertwined in a cosmic dance, and how our intuitive picture of reality is often flat out wrong. And I'm going to show you a few tricks and insights I've uncovered along the way that even most physics students never get to hear. Little gems from my notebooks, my lectures, my infamous "surely you're joking" adventures, and even experiments you've never seen. In certain thought experiments, it almost looks like information can travel faster than light, or that in the weird, wobbly world of quantum mechanics, light itself behaves in ways that would make your head spin. That's the kind of mind-bending territory we're about to explore. And if you think you understand physics already, I promise you don't, not until we go down this rabbit hole together. And it's not just about abstract science. Understanding light speed isn't just an intellectual exercise, it's a doorway to understanding reality itself. GPS satellites rely on these principles. Particle accelerators push the boundaries of energy using them. Even black holes, those cosmic monsters, obey these rules. The speed of light is woven into everything, and yet most people never even pause to marvel at the wonder behind it. That's why you must stay until the very end. In this video, I'm going to take you step by step through Einstein's mind, through the subtleties of relativity, and into the experimental weirdness that confirms the laws he laid down. But we're going to do it the Feynman way, not dry, not boring, and definitely not just equations. We're going to explore, to play with ideas, to bend our brains around the impossible, and yes, to laugh along the way. You see how I challenge conventional physics by asking the simplest questions. What happens? Why must it be this way? Could the universe really be so elegant? These were the questions that led me to uncover principles hidden beneath the surface of reality. And some of the answers are counterintuitive. They are shocking, they are beautiful, and they are waiting for you right now. So whether you're a seasoned physics fan, a student struggling through relativity, or just someone who loves the thrill of understanding the universe, this video is for you. We'll explore why the speed of light is the ultimate speed limit, uncover secrets that textbooks often skip, and reveal the astonishing consequences that come from a universe constrained by C. By the end, you'll not only grasp the limit, but you'll appreciate why it's one of the most profound mysteries in all of science. This isn't just about physics. This is about curiosity, the same curiosity that drove me to Nobel Prize-winning discoveries, to dissect the quantum world, to find joy in the tiniest particles and the largest ideas. Curiosity, when followed relentlessly, will take you to places that defy imagination. That's the real lesson I want you to take away. If you're ready to see the universe in a way that twists your mind and stretches your understanding, if you're ready to step into the shoes of a physics genius who saw reality differently than anyone else, then you're in the right place. Welcome to Feynman Flux, the channel where we dive deep into physics, where curiosity rules and where the mysteries of the universe aren't just explained, they're experienced. Hit that subscribe button because this journey is just beginning. And trust me, by the time we're done, you'll never look at light, time, or space the same way again. Have you ever thrown a ball while riding a bicycle and noticed how its speed seems to add up with yours? It feels obvious, right? If you're pedaling at 10 miles per hour and you toss a ball forward at 10 miles per hour, anyone standing on the sidewalk would say the ball is moving at 20 miles per hour. Simple, predictable, elegant. That's how classical physics works, or at least that's what we thought we understood for centuries. Back when I was a boy, growing up in Far Rockaway, New York, I had a fascination with speed that went far beyond the playground. I would take apart radios, watches, even old toy cars, not because I wanted to break them, although that often happened, but because I wanted to see how things moved, how energy flowed, how motion worked. My father encouraged my curiosity, even when I kept asking the same question over and over. Why does it happen this way? That curiosity, the relentless need to peek behind the curtain, is exactly what drives a physics genius. It's what later led me to Nobel Prize-winning work in quantum mechanics, but even in those early days, I was obsessed with the idea of motion. In the world of classical Newtonian physics, motion was simple and intuitive. Sir Isaac Newton, the physics genius whose ideas shaped centuries, gave us a universe that ran like clockwork. Velocities could just add up. If two objects were moving toward each other, their speeds would combine. If they were moving in the same direction, they would subtract. There was no limit, no cosmic speed cap. The universe felt safe, predictable. You could imagine a rocket going faster and faster, and in principle, nothing was stopping it.
And yet, that's where the first crack in our understanding appeared, because nature has a way of laughing at our intuitions. I discovered this myself when I started playing with light experiments as a teenager. Nothing was more fascinating to me than light. You see, light doesn't behave like a ball on a sidewalk or a car on a road. Light refuses to obey the simple rules of velocity addition, and back then nobody knew why.
Let me take you back to the 19th century, before Einstein, before anyone suspected that the universe had a speed limit. Physicists were in love with the idea of an ether, a mysterious, invisible substance that supposedly filled all space and carried light waves. It made sense at the time. If sound needs air to travel, surely light needs some medium too. And in this ether-filled universe, classical thinking seemed to work perfectly. Velocities could add up, speeds were relative, and the cosmos felt manageable. But experiments began to poke holes in this neat picture. The most famous, the Machiavelli experiment, tried to detect the Earth's motion through this ether by measuring the speed of light in different directions. You would expect, based on Newtonian ideas, that light would speed up or slow down depending on whether it was moving with or against the ether wind. But no matter what they did, the results were the same. The speed of light was constant. Every time, every measurement. That was a puzzle that sent classical physicists scratching their heads. I remember reading about this as a boy and thinking, how can the rules I know be wrong? That's the beauty of curiosity. It doesn't accept authority. I would spend hours building little contraptions, timing the tick of a clock, measuring shadows, trying to feel the rules of motion with my own hands. That tactile, hands-on approach is something they don't teach enough in physics classrooms. It's the kind of experimentation that leads you to question everything, even the ideas you thought were unshakable. In classical mechanics, the addition of velocities is intuitive because space and time are absolute. 1 second is 1 second, no matter who measures it, and 1 meter is always 1 meter. If you're moving fast, it doesn't affect the clock you're carrying or the ruler you measure with. You could imagine 2 rockets hurtling toward each other at nearly infinite speed, and classical physics would say, go ahead, just add the speeds. There was no ceiling, no universal speed limit, no barrier at all. The universe seemed infinite in its potential for motion. And then light comes along and says, not so fast. No matter how fast the observer moves, the speed of light remains the same. Doesn't add, subtract, or care about your velocity. That defiance of classical intuition is what fascinated me the most about light when I first encountered it. I remember being a teenager in my bedroom using mirrors and flashlights, setting up experiments with a precision that probably annoyed my parents, just trying to see if I could detect a change in speed. I couldn't, and that inability to fit light into the classical framework is exactly what would later lead Einstein to rethink space and time itself. Even as a young physicist, my own curiosity led me down similar paths. I loved taking things apart and putting them back together in ways that revealed deeper truths. Once I built a small-scale model of a cloud chamber just to see how particles move through a magnetic field. The way electrons bent, the way trajectories shifted, it was chaotic, unpredictable, and yet elegant. That early love for uncovering the invisible rules of motion prepared me for the moment when I would finally understand the mind-bending consequences of relativity. But back then, most people still trusted classical physics. After all, it worked perfectly in everyday life. Cars, balls, bicycles, they all obeyed velocity addition beautifully. It only failed when you reached speeds that approached light. That's the subtle trap. Our brains are wired to think in classical terms because that's what we see. We intuitively believe there is no speed limit because everything we observe seems to confirm it. And that's why the constancy of light was so revolutionary, it shattered centuries of intuitive thinking. It's a lesson I carried throughout my career. The universe doesn't have to match your intuition. As a Nobel Prize-winning physicist in quantum mechanics, I discovered that even the tiniest particles obey rules that seem absurd, even impossible, to our everyday experience. Electrons don't follow neat paths. Photons don't always travel straight lines. Energy exists in discrete quanta, and yet it all works beautifully and precisely. Understanding motion at high speeds is no different. Light doesn't play by classical rules, and recognizing that is the first step toward grasping relativity. Interestingly, many of my early experiments and thought experiments were inspired by sheer curiosity rather than formal study. I would ask myself questions that seemed silly. What if I could ride alongside a light beam? Would the universe freeze? I had no answers at the time, but asking the questions forced me to confront the limits of classical physics in a way that textbooks couldn't. That kind of playful curiosity is essential for any physics genius or anyone hoping to truly understand the universe. In classical Newtonian physics, speed seems limitless and velocities combine predictably. That simplicity is comforting but ultimately deceptive. The more you look closely at light, the more you see that the universe has a structure that refuses to be simple. Light speed is constant, and that constancy breaks the classical rules in a way that is both elegant and deeply puzzling. It's a riddle that has fascinated the greatest minds for over a century, and it's one I've spent my life exploring. So while we might have thought we knew everything about motion, about speed, about the way objects combine their velocities, light reminds us that our intuitions are fragile. That simple ball on a bicycle might obey Newton perfectly, but the cosmos, the deep cosmos, where light races across the vacuum of space, has rules that are far stranger, far more subtle, and far more beautiful than we ever imagined. That's the story of what we thought we knew about speed, the classical world that made sense, the Newtonian universe we trusted, and the first hints that our intuitions could fail when faced with the light-speed reality. You're pushing a car. At first, it moves easily, but the faster you push, the heavier it gets. Every inch forward demands more strength. No matter how hard you push, there's a point where you simply can't make it go faster. That's not a metaphor. It's exactly how the universe treats anything approaching light speed. Einstein's relativity changed everything we thought we knew about motion. Suddenly, energy, mass, and velocity weren't separate. They were entwined. The faster you go, the heavier you get. Not in the ordinary sense, but in a fundamental cosmic. Your mass increases, your clock slows, space itself bends around you. This is why rockets, no matter how powerful, can never reach or exceed c, the speed of light. As you accelerate, the energy required to go faster climbs toward infinity. Imagine trying to push that car and feeling it grow heavier with every push. Eventually, you hit a hard limit. That limit is light speed, and it's universal. It isn't just fast, it's woven into the fabric of space-time itself. I've explored these ideas throughout my life, from the Manhattan Project to developing quantum electrodynamics and my work with Feynman diagrams. Even in particle physics, nothing escapes this cosmic rule. Electrons, photons, and even the quirks of quantum mechanics all obey the speed limit.
It's mind-bending because it defies intuition. We grew up thinking speed can always add up, but the universe whispers a different truth. Light's constancy isn't a quirk, it's a law. The deeper you dig, the stranger it gets. And here's the kicker. This limit isn't a barrier to curiosity, it's a doorway. Once you understand it, the entire universe starts to make sense in ways that seem almost magical.
Stick with me, because next we're going to see how this cosmic speed limit warps time itself, and you won't believe what happens when you travel close to light speed.
Let me tell you something that blew my own mind when I first realized it, and it still blows minds today. Particles don't just take one path from point A to point B. Not one. They take every possible path, every twist, every turn, every zigzag you can imagine, and somehow when you add it all up, the universe decides what actually happens. That's the heart of my path integral approach, and it's as strange as it sounds.
I used to joke in my lectures, nature doesn't take shortcuts, it takes all routes, like a child exploring every hallway in a huge mansion. My students laughed, but underneath the humor was a deep truth. This approach wasn't just clever, it revealed the rules that govern everything, including light itself.
Here's where it gets really interesting. When you calculate all the possible paths a particle can take, something remarkable happens. Paths that would require faster than light travel cancel each other out. Mathematically, they interfere destructively. Only the paths that respect the cosmic speed limit survive. It's not a rule you impose, it's a law that emerges naturally from the math. The universe itself forbids faster than light motion.
I love teaching this because it captured curiosity in action. I'd show students how a photon seems to explore the entire universe at once, yet when you measure it, it always respects c. That's Feynman's charisma on display, turning mind-bending abstract math into something you can see and play with. Even in problem solving. In my work on quantum electrodynamics or sketching Feynman diagrams, this principle popped up again and again. The speed limit isn't just practical, it's embedded in reality's fabric. Every calculation, every particle, every quantum fluctuation obeys it. And yet the path to discovering it was playful, curious, and full of wonder, a signature of my approach to physics. Stick with me, because next we'll explore how this mathematical insight connects to time, space, and why light speed shapes the very rhythm of the cosmos. Imagine a universe where particles wink in and out of existence, where time stretches and shrinks, depending on how fast you move. That's the strange place where quantum mechanics meets Einstein's relativity. And yet, despite all this weirdness, the speed of light remains unbroken. Nothing, no particle, no signal, no message can travel faster. I used to tell my students, with a grin, the thing that's funny about the universe is that it's trying to protect itself from you. And in a way, that's true. Quantum electrodynamics, Feynman diagrams, my own problem-solving adventures, they all reveal the same law of causality. Cause and effect can't outrun light. If you tried to send information faster, the universe would cancel it out, just like paths in my path integral approach. This is where time dilation and length contraction come in. Move fast and clock slow, rulers shrink, and the universe bends around you. It's not magic, it's mathematics, it's reality, and it's exquisitely consistent.
Curiosity led me to see it, play with it, and teach it in ways that made students' jaws drop. The speed limit isn't just a number, it's woven into the structure of space-time, guarded by quantum weirdness itself, a cosmic rule that even the most mischievous physicist can't break. People love to imagine breaking the light barrier, tachyons, warp drives, spaceships zipping faster than c. I used to smile at these ideas in my lectures and say, it's fun to dream, but nature has a way of saying no. Even in thought experiments, the math from my path integrals and quantum electrodynamics keeps faster than light travel impossible. Energy skyrockets, causality collapses, the universe won't let you cheat. The speed of light isn't arbitrary, it's baked into space-time itself. Curiosity is encouraged, but Feynman's principles show some limits are fundamental, not just inconvenient.
So what have we learned? We started with classical intuition, velocities just adding up, a universe that seemed simple and predictable. Then Einstein came along and rewrote the rules with relativity, showing us that energy, mass, and velocity are intertwined, that light speed is a cosmic limit baked into space-time itself. And I, Richard Feynman, showed you how curiosity, problem-solving, and a playful approach to physics can reveal even stranger truths, particles exploring all paths, quantum mechanics protecting the speed limit, and the universe itself conspiring to uphold c. The speed of light isn't just a number on a chalkboard, it's reality's backbone. It shapes time, space, motion, and the very rhythm of the cosmos. It's a law that even imagination can't overtake, and yet exploring these limits could point toward the next revolution in physics. Remember, curiosity matters. Question, experiment, and think differently, just like I did. Let my curiosity, my teaching methods, and yes, my quirky problem solving be your inspiration in physics and in life. If this journey through quantum mechanics, relativity, and the genius of Feynman sparked your mind like this video, comment your questions and subscribe to Feynman Flux. Dive deeper into the mysteries of the universe with our other videos. Explore, wonder, and never stop asking why. The universe is waiting, and it's more incredible than you ever imagined.